In this video, we are going to discuss about lemma 1. So that is let B be a basis. Let B be a basis for a topology. For a topology on X. For a topology on X. And let tau be defined by. Let tau be defined by. Tau be defined by. Tau is equal to set of those subsets of X such that X for each X belongs to U. For each X belongs to U, there exists a B belongs to B. There exists a B belongs to B. B belongs to B such that X belongs to B, which is contained in U. Then tau is a topology. Then tau is a topology on X. Okay, so this is the statement. So here given that let B be a basis for a topology on X. They're given the basis for a topology. Now I am defining the tau by I am taking set of those subsets of X such that subset satisfies this condition, that is for each X belongs to U, there exists a B belongs to B such that X belongs to B, which is contained in U. So okay, then we need to prove that tau is a topology on X. Okay, that is here we know that every elements of tau are open sets. So now we are going to prove that openness of sets, that is we need to prove so to prove that tau is a topology, we need to prove three conditions. The first condition is empty set and X itself are in tau, and the second one, tau is closed under arbitrary unions, and the last point is tau is closed under finite intersections. Okay, we need to prove three conditions. So the proof first, if U is empty, then the openness condition satisfies vacuously. Since it is empty, so we know that element of tau are open sets. So this is nothing, we call this one is openness of a set U. So if U is empty, then this condition satisfies vacuously. Okay, the next one, the next condition, that is if U is X itself, so then from the definition, by the definition of B, that is basis, for each X belongs to X, there exists B belongs to B such that X belongs to B, but which is a subset of X. So therefore the openness condition satisfies, therefore X belongs to. So observe, in place of U, if you replace X, so we prove this condition, that is for each X belongs to X, there is a base element so that X belongs to B, which is contained. In place of U, we have a X here, therefore X belongs to U. That is first condition is satisfied, that is empty set and X itself are in tau. Okay, so we need to prove the second condition. So we need to prove the second condition, that is next. So that is to prove that tau is closed under arbitrary unions. Tau is closed under arbitrary unions. For that one, let I am taking arbitrary subcollection. Let u alpha belongs to J, be any arbitrary be any arbitrary subcollection of tau. Be any arbitrary subcollection of tau. Let u alpha be any arbitrary subcollection of tau. So put u is equal to union of u alpha belongs to J. So what we need to prove that? We need to prove that union of this collection belongs to tau. That is to prove that u belongs to tau. But to prove that u belongs to tau, we need to prove that is for each x belongs to u, there exists a b belongs to b, such that x belongs to b which is contained in u. So this is from the definition. So if you want to say that an element are in tau, so an element is in tau, which means that for each x belongs to u, there is a basis element such that base element containing x and that base element contained in u. So this is from our statement. So this is the statement, that is, if you want, so an element u in tau means which must satisfy this condition. Okay, that is for each x belongs to u, there is a basis element b belongs to b, such that x belongs to b which is contained in u. So now here we need to prove that u belongs to tau. To prove that u belongs to 2, so to prove u belongs to 2, I need to prove this condition. Okay, so for that one, I am taking an arbitrary element x in u. Let x belongs to u be arbitrary. Since x belongs to u, which is equal to union of u alpha belongs to J, then x belongs to u alpha for some alpha belongs to J. So the reason is, here observe, here I am taking u as union of u alpha belongs to J. From the definition of union of u alpha, that is arbitrary union of some sets u alpha, x belongs to union of u alpha means x belongs to u alpha for some alpha. So if x belongs to intersection of u alpha, then x must belongs to u alpha for each alpha. Here x belongs to union of u alpha, therefore x belongs to u alpha for some alpha. Okay, but u alpha is in tau. I am taking elements of u alpha. I am taking elements u alpha from tau. I am taking in the arbitrary subcollection of tau means each u alpha are in tau. So but u alpha belongs to tau for each alpha. Belongs to J. So therefore x belongs to u alpha for some alpha implies that there exists basis element. Okay, there exists basis element b belongs to b, such that x belongs to b which is contained in u alpha. But observe here, u alpha is contained in union of u alpha. Therefore x belongs to b now which is contained in union of u alpha belongs to J. Therefore x belongs to b which is contained in u, which is nothing but 1. Therefore we prove the condition. Therefore u belongs to tau. Therefore tau is closed under arbitrary unions. Tau is closed under arbitrary unions. So, okay, now to prove the last condition. So finally let I am taking, that is to prove that tau is closed under finite intersection. For that one, let uk k from 1 to n be any finite subcollection of tau. Okay, now to prove that intersection of uk k from 1 to n are in tau. This is an idea. So I am using induction here. So by induction on n, so we know that put n is equal to 1, then u1 belongs to tau. So here there is nothing to prove. Here. That is, if you take any finite subcollection, their intersection must be in tau. Okay, that's our aim. First I am taking n is equal to 1. So clearly u1 is an element of tau, therefore there is nothing to prove here. That is, u1 belongs, no need to prove that u1 belongs to tau, since u1 is already in tau. I am taking u1 from tau only, therefore here there is nothing to prove. Put n is equal to, if n is equal to 2, that is, then I am taking two elements u1 u2 are in tau. Okay, now what we need to prove that? To prove that u1 intersection u2 are in tau. u1 intersection are in tau. So since u1 belongs to tau, so from the definition, for each x belongs to u, there exists a b1. I am taking here b1 belongs to b, such that x belongs to b1 which is contained in u. Okay, so I am taking say 1. Similarly, since u2 belongs to tau, implies for each x belongs to, sorry, this is u1, this is u2, there exists b2 belongs to b, such that x belongs to b2 which is contained in u2. This is u1. Say 2. Okay, so now what we need to prove, that our aim is to prove that u1 intersection u2 are in tau, right? So for that one, so to prove this one, what we need to prove, that we need to prove that for each x belongs to u1 intersection u2, there exists b belongs to b, such that x belongs to b which is contained in u1 intersection u2. So this is true for each x belongs to u1 intersection u2. Therefore I am taking an arbitrary element. Let x belongs to u1 intersection u2 be arbitrary. So x belongs to u1 intersection u2 implies x belongs to u1 and u2. So from 1 and 2 there exist b1 and b2, such that x belongs to b1 which is contained in u1 and x belongs to b2 which is contained in u2. Therefore x belongs to b1 intersection b2 and which is contained in u1 intersection u2. I am taking b1 intersection b2 is b which is contained in u1 intersection u2. So therefore it satisfies the condition. Therefore u1 intersection u2 are in tau. Okay, and I am assuming that u1 intersection u2 intersection uk minus 1 are in tau. ಸೊ ಸೊ ನಾನು ಇಲ್ಲೇನು ಮಾಡ್ತಿದ್ದೀನಿ, ಅಪ್ ಟು k-1 ತನಕ ಎಲಿಮೆಂಟ್ಸ್ನ ತಗೊಂಡು ಇಂಟರ್ಸೆಕ್ಷನ್ ಮಾಡಿ ಅದು ಟವಲ್ ಇದೆ ಅಂತ ಹೇಳ್ತಿದ್ದೀನಿ. ಸೊ ಇಂಡಕ್ಷನ್ ಪ್ರಕಾರ ನಾನು ಕಂಡೀಷನ್ ಸ್ಯಾಟಿಸ್ಫೈ ಮಾಡ್ತಿದ್ದೆ ಅಂತ ಹೇಳಬೇಕು ಅಂತಂದರೆ ಅಪ್ ಟು ಕೆ ತನಕ ಆಗುತ್ತೆ ಅಂತ ಹೇಳ್ಬೇಕು ಅಷ್ಟೇ. ದಟ್ ಈಸ್ ಕನ್ಸಿಡರ್. ಸೊ ನಾನು k-1 ತನಕ ಟವಲ್ ಇದೆ ಅಂತ ಹೇಳಿದ್ದೀನಿ. ಸೊ ಕನ್ಸಿಡರ್ u1 ಇಂಟರ್ಸೆಕ್ಷನ್ u2 ಇಂಟರ್ಸೆಕ್ಷನ್ uk-1 ಇಂಟರ್ಸೆಕ್ಷನ್ uk ಇಷ್ಟಕ್ಕೂ ಆಗುತ್ತೆ ಅಂತ ಹೇಳ್ಬೇಕು ನಾನು. ಅಪ್ ಟು ಎಲ್ಲಿ ತನಕ ಯು ಕೆಗೆ ಆಗುತ್ತೆ ಅಂತ ಇದನ್ನು ಬೇಕಾದ್ರೆ n ಮಾಡ್ಕೊಳ್ಳಿ, ಅಪ್ ಟು un-1 n-1 n. ಓಕೆನಾ. ಸೊ ನಾನೇನಂತ ಹೇಳಬೇಕು, ನಾನು ಅಪ್ ಟು ಇಲ್ಲಿ ತನಕ ಇಂಟರ್ಸೆಕ್ಷನ್ ಮಾಡಿದ್ರೂ ಯು ಟವಲ್ ಇದೆ ಅಂತ ಹೇಳ್ತಿದ್ದೀನಿ. ಬಟ್ ನಾನು ಈ ಎಲಿಮೆಂಟ್ ಮಾಡಿದ್ರೂ, ಸೊ ಇವಾಗ ನಾನು ಅಪ್ ಟು n ತನಕ ಮಾಡಿದ್ರೂ ಅದು ಟವಲ್ ಇದೆ ಅಂತ ಪ್ರೂವ್ ಮಾಡಬೇಕು. ಸೊ ಇಂಡಕ್ಷನ್ ಏನು ಮಾಡ್ತೀವಿ, ಫಸ್ಟು ಬೇಸ್ ಆಫ್ ಇಂಡಕ್ಷನು ಎನ್ಗೆ n=1 ಕೊಟ್ಟಾಗಲೂ ಟ್ರೂ ಆಯಿತು, n=2 ಕೊಟ್ಟಾಗಲೂ ನಾವು ಪ್ರೀವಿಯಸ್ ಸ್ಟೆಪ್ಪಲ್ಲಿ ಏನು ಮಾಡಿದ್ವಿ, u1 ಇಂಟರ್ಸೆಕ್ಷನ್ u2 ಟವಲ್ ಇದೆ ಅಂತ ಆಯಿತು. ಸೊ ನಾವೇನು ಮಾಡ್ಕೊತೀವಿ, ಅಸ್ಯೂಮಿಂಗ್ ದಟ್ ಅಪ್ ಟು n-1 ತನಕ ಕೂಡ ನೀವು ಎಲಿಮೆಂಟ್ಸ್ನ ಇಂಟರ್ಸೆಕ್ಷನ್ ಮಾಡಿದ್ರೆ ಟವಲ್ ಇದೆ ಅಂತ ಆಯಿತು. ಇವಾಗ ನಾನು ಏನಂತ ಪ್ರೂವ್ ಮಾಡಬೇಕು, ಅಪ್ ಟು n ತನಕ ಆಗುತ್ತೆ ಅಂತ ಮಾಡಿದ್ರೆ ಬೈ ಇಂಡಕ್ಷನ್ ಯಾವುದೇ n ತಗೊಂಡ್ರೂ ಆಗುತ್ತೆ ಅಂತ ಆಗುತ್ತೆ. ಓಕೆನಾ. ಸೊ ಅದಕ್ಕೆ ನಾನು ಕನ್ಸಿಡರ್ ಮಾಡ್ಕೊಂಡಿದ್ದೀನಿ. ಬಟ್ ಆದರೆ ಇಲ್ಲಿ ಒಂದು ಏನಪ್ಪ ಅಂತಂದರೆ, ನೀವು ಈ ಎಲಿಮೆಂಟ್ ಇದೆ ನೋಡಿ, ಇದನ್ನು ಹೆಂಗೆ ಬರಿಬೋದು ಅಂದರೆ ಇದನ್ನು ಒಂದು ಎಲಿಮೆಂಟ್ ಥರ ಬರ್ಕೋಬೋದು ಅಂದರೆ ನೋಡಿ, ವಿಚ್ ಈಸ್ ಈಕ್ವಲ್ ಟು u1 ಇಂಟರ್ಸೆಕ್ಷನ್ u2 ಇಂಟರ್ಸೆಕ್ಷನ್ un-1 ಇಂಟರ್ಸೆಕ್ಷನ್ un. ನೋಡಿ ಇದೊಂದು ಎಲಿಮೆಂಟಾಗಿ ಬರ್ಕೋಬೋದಾ, ಇದು ಟವಲ್ ಇದೆಯಾ, ಇದು ಟವಲ್ ಇದೆಯಾ. ಸೊ ವಿಚ್ ಈಸ್ ಬಿಲಾಂಗ್ಸ್ ಟು ಟವ್ ಬೈ ಪ್ರೀವಿಯಸ್ ಸ್ಟೆಪ್. ಸೊ therefore ಏನಾಯಿತು ನಿಮಗೆ, ಸೊ therefore intersection of uk k from 1 to n belongs to tau for all n by induction on n. Therefore tau is closed under arbitrary intersection. So arbitrary intersection, therefore tau is a topology. So therefore tau is a topology on X. Okay, thank you very much.